Rami, who is our engineer in Bordeaux. So this is actually, it's considered now that, like in practice, VRPs are solved by heuristics, and exact approaches are there mainly for theoretical purposes, and also to obtain optimal solutions and just to check how good are the heuristics. But in practice, we really use heuristics. While this is mostly true, here I still would like to advocate for that. Due to some recent progress, there is probably now some room for exact approaches, even in practice. So talk will be a bit more general than that. So I will start with a very brief overview of exact state-of-the-art algorithms for vehicle routing, and give you some hints about their performance. Then, of course, we cannot solve large instances with exact approaches, and so second part will be devoted to some math heuristics which use exact approaches to solve large instances, and this also related to our participation to the DIMACS challenge last year. And I finish with the latest work we have done on trying to make our work practical and easy to use for you. So when we talk about exact approaches, especially state-of-the-art exact approaches, so we always think about set partitioning formulation for the problem, in which the set of feasible paths we represent as a set of resource-constrained paths in some graph or in several graphs. And then using this bijection between routes and the paths, so we can come up with this formulation where we can have two types of variables: these arc variables x and the path variables lambda. And then, so what we want to minimize, so this is formulation for CVRP, for example. So we minimize the total cost such that every client should be covered exactly once. And there are some, the number of routes is limited. And here we have a linking between the arc variables and path variables. This linking we call ourselves mapping. We map arcs, we map arc variables to the arcs in the graph. So here the mapping is very simple, is one-to-one, but in more complex applications we can have a more complex mapping. And also, to have a state-of-the-art performance, we are obliged to use cuts. Without cuts, we cannot obtain it. And there are two kinds of cuts we have: the cuts which are expressed over the arc variables, which we call robust cuts, and the cuts which are expressed in terms of the path variables. They are what we call non-robust cuts because they impact the solution algorithm behind. And these cuts are essentially free to us. And so the beauty of this formulation is that this formulation is really, really general. Because, for example, you can express a lot of additional constraints conveniently. For example, the inter-route constraints can be expressed just by adding additional variables, additional constraints to this MIP. And intra-route variable or additional intra-route constraints can be added by adding additional resources or changing resources in the definition of the feasible paths. And so the approach is general for many VRPs. And so how we solve that? So first of all, as we do usually in MIP, we need to solve linear relaxation of this problem. Linear relaxation is solved by column and cut generation. So here I give a small example. Here I express the mass of the client. So this is CVRP. I express the mass of the clients in percentage from the vehicle capacity. So we have one continuous variable per feasible route, and we generate these variables dynamically by solving the pricing problem, which is a resource constraint shortest path problem. So we do this iterative process until the convergence. But as I said before, to have state-of-the-art performance, we really need to add cuts. And so we add cuts. So here I give examples of this cut. So this is an example of a robust cut. So here, if you take these three clients, you can notice that the sum of the demands is larger than 100%. And this means that these three clients should be covered by at least 2 vehicles, and we can have a constraint that number of vehicles entering this set of clients is greater or equal to 2. So this is robust because we can express it in terms of the arc variables. We just sum up all entering arcs to this subset, and we say that their sum should be greater or equal to 2. If we take subset of these three clients, so it's more or less the same situation, except that the sum of the demands now is less than 100%, so we cannot add the same constraint there. But we can notice, for example, we can add a different constraint. Here is that the number of vehicles serving at least 2 of these three clients should be less equal to 1. And this is a non-robust constraint because we can express it only in terms of the route variables. And so, these constraints I express it in terms of the nodes. So here nodes corresponds to customers, but we can generalize this approach to a more general case, whether we introduce this new concept, packing sets. Packing sets is a collection of vertices or arcs. And in some applications, one customer is represented not by a single node, not by a single node, but for example, if you have a heterogeneous fleet vehicle routing, you have one node in every graph, where every graph corresponds to different vehicle type. If you have an arc routing application, you have one customer is represented by two arcs. You can serve the customer in both directions. Or if you have like VRP with where every customer can have alternative delivery locations, you will have different nodes representing the same customer, and all this can be represented with this packing sets. You just add the same the nodes or arcs corresponding to the same customer to the same packing set, and you apply the same machinery. And we use packing sets not only for cuts but for other components too. So this is the so here we need to solve this research constraint shortest path. So how we solve it? So we solve it in a standard way, so it's well known. We solve it by labeling algorithm, which is a dynamic programming algorithm. So it's based on enumeration of partial paths, and it heavily relies on the domination in order to avoid the combinatorial explosion. We also use the techniques like bidirectional search, buckets, which allow us to decrease the number of dominance checks. We use completion bounds also to remove unpromising labels in addition to the domination. So the both work nice together. So this is the standard way to solve the RCSP. But again, in order to have state-of-the-art performance, we need to do something more. And so in the state-of-the-art algorithm, so we need to add a mix of restriction and relaxation. So here we use problem restriction. Here we restrict the problem without losing optimality, and we do it as often as done in mixed integer programming using reduced cost arguments. And so what we do, we just remove arcs, and sometimes we remove the whole paths, which we are sure will not participate in any improving solutions. And we use for that the primal dual gap. So if you consider this illustration, so you should pay attention only to this line here. So here, the H point here, it corresponds to arc, and the Y coordinate corresponds to the lower bound plus the reduced cost of this arc. That's okay, a bit more complex than that, okay? And you can see this is your lower bound, and this is the optimal solution. And so if your current non-optimal solution exactly equal to the optimum, you can remove more than 80% of the arcs. But the worse is your known solution, the less arcs you will remove, and larger time will take the pricing. And so this shows that this primal dual gap is very, very important. And so here there is a nice synergy between exact algorithms and the heuristic algorithms, because heuristic algorithms allow us to have better solutions and to speed up our calculations. And so I said we use a mix of restriction and relaxation. So for the relaxation, what we use the limited memory concept. Here we can take advantage of that because we have a very specific resource constraint shortest path instances, where we have almost all resources actually are local. So for example, here you have, these nodes in gray are the only nodes among all nodes which have non-zero resource consumption. And so we define a so-called memory around these special vertices, and when we follow the path in the pricing, we track resource consumption only inside the limited memory. And once we're outside the limited memory, we forget resource consumption. And this allows us to speed up a lot the pricing, because for any node, actually the overall number of resources are very large, but the number of resources tracked at any given node is much, much smaller. So this is much faster. And of course, it's the memory is not really fixed. We try also to set it dynamically, and we improve this relaxation after each column generation convergence. About heuristics, yeah, of course, in practice, you should rely on heuristics too, and we do it here. But the problem is that the whole approach is quite generic, and we are more or less obliged to use generic heuristics. And these generic heuristics, which are basically for column generation, are diving and restricted master. They're not very efficient. First of all, they're efficient only, let's say, for instances with short routes. And if you have larger routes, diving is not efficient because we work constantly with the relaxation of the problem. And when you start to fix routes, eventually no route will be feasible, and you will have nothing to fix, and you will be stuck. And so that's why we almost never use diving heuristic for vehicle routing. What we use is we use restricted master heuristic, but again, we are obliged, before running restricted master heuristics, we are obliged to do preliminary path enumeration with the false primal dual gap in order to have the feasible routes, and then we work with feasible routes. And concerning the branching, you probably never want to branch if you want to solve the problem heuristically, but still there are some branching decisions which are very important. For example, the number of vehicles you use, the type of vehicles you use are very important branching, and they change the dual value a lot. And so even if you want to solve your instance heuristically with heuristic branch content price, the branching can be important, especially on very aggregated decisions. So this is of course what I presented before. It's not our work. It's the work which was done by generations of researchers, and which was started right back to '64 with the first set partition formulation for CVRP. There was some important work done in '80s, some very important work done like 20 to 15 years before. And so this slide is just to show you that of course, this is a very biased selection of important works, and there were much more important works in the subject. And our machinery now is based on many works and many researchers. So this is I go to the performance. So what's the largest instance we were able to solve up to now is the instance with 865 customers, but of course we solve it in 20 days. Of course, you never want to wait 20 days to solve it. So, but it's nice to, from a theoretical point of view, what you can do. Yeah? And also, it's for this exact approaches, what is very important is the average length of the routes. So what did we do? We compare the branch cut and price and the branch and cut approach to solving 100 customer instances depending on the size of the average route in the instance. And you can see that, okay, the branch cut and price is clear winner here, but starting with very long and ultra long routes. So ultra long means that the average route size is greater than 25. The branch and cut becomes more efficient, and here, if you continue this line, you will have a TSP, and of course for TSP, branch and cut will be much more efficient. And so, yeah, you can see that this is probably the instances you can hope to solve, and these are probably not anymore. And yeah, actually, all these 10,000 instances with 100 customers was solved recently by Eduardo and Joao, who are present here. And this is typical solution times we have for branch cut and price. So this is the instance size. This is the solution time, the log scale. So what you can see here is that probably in practice, up to 100 customers is a reasonable size to solve, I think, because it's never exceed like 1 minute. But of course, this is and what is larger than 100, on average, is okay, but you can have some instances which are very hard to solve, of course, due to the fact that the problem is NP hard. And but of course, this is the ideal situation for us, because this is like here we suppose that we know the optimal solution right from the start, and here we just prove its optimality. Of course, in reality, it's not the case. But usually, if you don't know a good feasible solution right from the start, you can probably multiply the times by a factor of 2, 3, sometimes 5. Yeah. But it's reasonable. It's not like it will not be 1 order of magnitude larger, so maybe 2, 3 times larger. And so you can see that, okay, with BCP you can solve up to 100, but what to do if you have a larger instance? So we had this recent work about pop music math heuristic. So we use this quite known heuristic, which is called pop music. And here the idea is very, very simple. I think many of you have used similar heuristics in your career. You take a known solution, you take some seed client, and you grab the route which are close to the seed client. And this closed route, they will define the sub-instance of your problem. You take this sub-instance and you solve it again. And we saw in our case, we solve it with branch cut and price, and you can hope to improve your solution. And what is important here is that in our case, when you solve the sub-instance by branch cut and price, it's very important to increase the size of the sub-instance iteratively. So you should start with sub-instances which are really small. While your overall solution has a bad quality, the sub-instances should be small, because otherwise you will not be able to solve it to optimality. But once you cover like the small neighborhoods, your solution quality increases, and you are able to solve a larger and larger instances. And so it's important to have this steady increase of the sub-instance size. So this is our design choices. As I explained, we increase progressively the subproblem size. And also we use the heuristic BCP because as we saw before, there will be always instances you will not be able to solve, and we need to set at least the time limit for that. And okay, you can say, okay, but you can also solve the subproblems by heuristic. Why you should use branch cut and price? And actually, yeah, that's what we did for the challenge. We did not use branch cut and price. We use the Thibault heuristic. And also these types of heuristics were very extensively studied in the recent work by Santini et al. So if you're interested, you should look this this reference. But what's the advantage of using the branch cut and price to solve the sub-instances? It's basically because it's more generic. Because, for example, the Thibault heuristic is very specialized to CVRP, and if you have CVRP, probably you should not use BCP, of course. But if you have a problem which is not CVRP, which is less classic, probably the branch cut and price will be better. At least you will be able to implement it much faster. And also, so what is if you use heuristic? There is also a question: what will be the termination criteria when you solve the subproblem? And this question is set down automatically. If you use branch cut and price, you just solve it and you wait until it's done. So there is no problem in that. Yeah, as I said, okay, this is a comparison of our pop music heuristic with the best heuristic for CVRP. So you can see that we can be a bit better than the Thibault heuristic, but starting from 2 hours time limit. So basically it's not practical. And so why is it interesting? Is that if you use BCP, as I said, the formulation is quite general, so you can just model your problem differently, and you automatically have a heuristic approach for a different problem. And so, for example, we did it for CVRP with backholes, and when we compare with the state-of-the-art heuristic, so we can improve quite a lot the best known results. The same for heterogeneous fleet, so we can improve a lot the best known results. Of course, the times here are quite large, but you can mitigate it, I think, with a nice parallel implementation, because here our implementation is not parallel at all. So we can do much better with a parallel implementation. Okay, so now it's nice that we can do all this kind of stuff, but probably for you it's much more interesting whether you can do all this stuff. Yeah. So whether we can do it's not as interesting, but actually the question is yes to some extent. So we try to make use of state-of-the-art branch cut and price as easy as possible for you. And recently we released this VRP Solver Easy Python package, and so it's a layer above the VRP Solver, which is a best exact solver for VRP. So we have like this 4-layer implementation where we have VRP Solver Easy, which is a Python interface with a simple interface. We have a C++ or Julia VRP Solver with a quite involved interface, so we thought that if this interface is easy for us, it will be easy for everybody, but it's not the case at all. And so, yeah, we did not have as much users as we expected without, so maybe with VRP Solver Easy we'll have more. And behind there is a Bob code, there's generic branch cut and price and solver, with a C++ code which uses Cplex or CLP, and also behind there is a resource constraint show the path solver, which is in C++. So there is 4 layers. And in terms of the licensing, it's not very, yeah, I mean, what is VRP Solver Easy is completely free, open source, which is below is not. But if you get VRP Solver Easy, you have everything here in the compiled form. Yeah? Also, for example, if you have Bob code, you have everything here in the compiled form. So this is closed source. There is a licensing issues because the code was started when I was doing my sabbatical in Brazil. And my advice to you, if you go to sabbatical, never start in important code, because later you will have problem with licensing that. But we're trying to improve the situation here. So what we have here is that in the easy interface we have depots, vehicles, customers. Here we have variables, constraints. Here we have Sven label buckets. So here's a 50-year-old mess, but But one of my co-authors, Arthur Pessoa, is trying to now to replace Bob code by Julia code, which is much more robust, much more industrial quality, and much more tested. But this is what we have for the moment. But I can assure you that's VRP solver easy, and it's quite well tested. This source code is there, and so the interface is, as I said, easy because it uses DPOS customer vehicles. Basically, you don't need to know how to model your problem as a MIP to use it. We cover quite a lot of VRP variants, and potentially we can cover even more variants, but we will wait what will be the demand for them. For the moment, it's a lot of work, and we don't know where it pays off. And for the moment, we just propose this one. So it's basically it's a compromise between generality and simplicity. So this is the code example for CVRP. You can see that you add dput, add customer, add link, add vehicle type, and you can solve. And this is some computational results for VRP Solver Easy. So for 3 problems, and you can see again that these are up to 100 customers. The results are quite nice. So we initialize the VRP Solver Easy with a solution obtained by OR Tools. Okay, and we were quite surprised, but okay, OR Tools quality is okay for CVRP, but once you go to time windows or HVRP, the quality drops dramatically. We were quite surprised with that, but we can do much better than that. For example, here we pass from 14% gap to 0.14. You see the gap is quite improved quite a lot. But of course, this is up to 100 customers. If you go up to 200, yeah, it's less spectacular. Yeah? And so to the last slide. So this is the practical relevance. So what is possible now is that it's finally easy to use, because up to now the branch cut and price just to use it was really difficult. Now it should be much easier, at least for some of the problems. And what we can expect to be useful in practice, it's for small, moderate size, up to 100 customers, so a bit more if your routes are not that long. And for these instances, okay, the best heuristics are, we cannot compete with the best heuristics, but best heuristics are very specific. But we can compete with the generic VRP solvers like OR Tools, local solvers. We are more efficient than them, okay, for these kinds of instances. And what we in future, so we still need a better quality code. As I explained, the parallel implementation of the math heuristics is really required for the larger instances. And also, as I said, that there is a nice synergy between heuristics and exact approaches, because we can use the solutions from the heuristics and use it in the exact. I think that's the opposite. It can be useful. I think that the dual information we obtain in column and cut generation is a really valuable information which can improve the heuristics. So this is, I think that's a direction to pursue. So usually people now trying to use information from machine learning, and they forget about more classic approaches. So probably you should not forget everything, and you should, still use something classic. Yeah, thank you very much.
More questions?
Did you have the full references somewhere?
I don't know if the organizer will put the presentations online or not. But I have all the references right here. Yeah. I can give you the presentation.
Any other questions? in the last item here, did you ever try to use it as a heuristic where you would allow longer routes, but are not exactly separating?
Sorry, can you repeat that?
Concerning the last point,
This one.
as a hybrid heuristic,
Yeah.
did you ever try to use it when you would allow also longer routes, but you're not necessarily exactly generating routes? Or give up at some
Yeah,
point?
longer routes are not as good for exact approaches, but yeah, but still can be, yeah, it's totally possible. Yeah, this is like perspective we did not explore that much, but I think that this should be explored and probably more people should be involved. Yeah.
The robust constraint and the non-robust constraint that you have, there must be exponentially many of them. So what do you use to separate them? Do you separate them? Do you solve a separation problem and then map them? Or?
Yeah, that's is usually that they we solve them heuristically. Yeah, that's as done in MIP solvers usually. Yeah, that's no point to separate exactly because it's NP hard and heuristics usually work very well.
Just one comment. It's nice that finally there's something very easy to use, and which is very general. There are many variants that are covered. So if you have problems with no more than 100 customers, you can expect to solve in a few minutes. So which can be reasonable for many applications. Okay, thank you.